All right, good morning. Welcome to, as CEO Lee put it, welcome to Fortuitous Friday. Just before we get started, just a couple of quick announcements. The first thing is that Sam Van Rooven and Chi-Ming Cheng had switched the order of the talks. So this morning we'll hear from Chi-Ming Cheng. And for the speakers, the talks are scheduled roughly 1 hour with 15 minutes at the end for questions. If you're wondering where the clock is over there, it's back there. So the speaker can see it. And so the reminder is if we start at 9, you talk until 10 or something like that, give or take a few minutes, and then we'll have room for some discussions afterwards. If you're listening to the talks, there's no reason to stare at a clock. You should be staring at the speaker, so it's perfectly okay. So we were very happy to have our first speaker today is Hong Liu, and he'll tell us about the holographic origin of wormholes.
Okay, thanks for the invitation to this very nice conference. And it's always a great pleasure to be back at Michigan. So so this talk will be mostly about a paper which I recently finished in December, which is about, a part of it is about understanding the holographic origin of wormholes. So for holography, we have this fundamental relation between the CFT partition function and the gravitational partition function, which is supposed to be valid at full quantum gravitational level. And so here M is some compact Euclidean manifold you can put your CFT on, and can be disconnected or have can be topologically non-trivial, etc. And the relation, a fundamental relation between this identification of the parameter is that the n square, which characterizes the number of degrees freedom on the CFT side, is related to the Newton constant by 1 over G Newton. So this relation, even though it's a very powerful and important relation, but since we cannot really calculate a gravity at the quantum gravitational level, say, not even be able to define it most of the time. So a more useful relation which people have been looking at is this, the G Newton goes to 0 limit, which is the semi-classical limit of this gravity partition function. Okay. And so there have been huge amount of work, of course, in establishing this relation, and there are many, many successes. Okay. But here, I want to emphasize the limit here should not be understood as the strict, say, the pointwise limit as normally mathematically, but should understand, one should understand it as the identification of the symptotic expansion on both sides respect to their parameter. So for example, on the gravity side, we normally formally write the gravitational path integral, or a partition function, as a gravitational path integral. Okay? But of course, defining this path integral beyond no dimensions is, it's not really well defined. Okay, there are all kinds of problems with defining this path integral, and we know that for string theory, this gravitational path integral is not enough. And but in the semi-classical regime, we just treat this path integral as a device for doing set point approximations. Okay. And so the general structure, so you just find the classical solution of your the Euclidean action, and then you just expand the G Newton around. You just expand around that set point, and then you sum over all possible set points with this boundary condition that your Bach manifold, the boundary should be given by n. Okay. So this is the classical value action of the saddle, one loop, two loop, etc. And similarly, so this I sums over all different saddles. So in principle, we should include all subdominant saddles, okay, not just the dominant one, but all subdominant saddles. So on the CFT side, it's believed that the same structure applies. That the CFT partition function, you can write it in terms of a symptotic expansion in 1 over n squared. And again, you have the similar structure, so often you can write the CFT partition function in terms of some kind of matrix integral or etc. And then you have large n saddle point. Okay, so again, you sum up all the saddle point and the fluctuation around the saddle point, etc. And then this relation, then it's a relation that these two expressions, they should agree order by order. Okay, so the sum of the saddle point should agree, and the value, the exponential should agree, and one loop, two loop, etc. So in special cases, when people have been able to make this kind of a comparison in great detail. Okay, so that's one of the great successes of this relation. But they have also been indications that this actually relation cannot be correct, okay, at the fundamental level. And so one of the first problem, which already surfaced immediately after the discovery, which hinted by Witt and Yao, and then later sharpened by Martin and Maus, is this factorization problem. So you essentially look at take M to be disjoint union of two manifolds. And then by definition, the CFT partition function should factorize. And this factorization should not depend on whether you take the large n limit. Okay, in the large n limit, it should also factorize. So that means that in a G Newton goes to 0 limit, the gravitational partition function should also factorize. But on the gravity side, you can easily find solutions which they don't factorize. And so you have this kind of wormhole solutions which connect M1 and M2. Okay. And so I emphasize when you compare the two sides, you should compare all saddles, okay, including exponentially subdominant saddles. And so even if there's an exponentially small contribution from the wormholes, and this relation is spoiled. Okay. And you can just, it's not enough, just look at the leading order, say they factorize. And so this creates a puzzle. So this puzzle is partially is better understood in the low-dimensional gravity, where you can just define the gravity using path integral. Okay, in the low-dimensional gravity, for example, like JT, you can just just define the JT gravity using path integral, and then you can just calculate it. And then one shows that then this related to the ensemble averages on the CFT side. And then if you do the average, then of course on the CFT side, they no longer factorize. Okay. So so in the JT gravity, this problem is not there. And so there are also indications that maybe for pure ADS3 gravity, which we can also define using path integrals. And in principle, path integrals and maybe due to some average CFTs. And then again, this problem will be addressed. But in higher dimensional gravity, and in gravity theory from string theory, for example, even when you consider two-dimensional gravity, if that comes from string theory, and then we know that the gravitational path integral is not enough. Okay, you must include something else. And so it's not clear, so it's not clear what's the story here. Okay, and there are two logical possibilities. So one logical possibility is that the secretly gravitational expression should also factorize. And actually, in order for this duality to be true, the gravitational expression has to factorize. Okay, it's because on the CFT side, if you believe that is the correspondence. Okay. And so people have speculated many possibilities for this factorization, say whether we miss something in the gravitational path integral, or maybe there should be some prescription, you should exclude wormholes. Okay. And but but this idea but has not really a convincing way which this has been able to solve a problem, say, in the realistic situations. And another possibility is that some kind of average or cross-graining is needed when you relate the CFT to gravity. Okay, in other words, just you imagine, just like in JT situation, somehow the gravitation, the gravity is mapped to some average of your CFT, and then you don't have the factorization problem anymore. But so far, people don't have an intrinsic way to define what this bar means on the CFT side. So right now, this bar is just used as a device to essentially, right now this bar just used as a definition essentially just use gravity as a definition for what this bar means right now. Okay. And so there's no intrinsic boundary definition so far. Okay. But people have tried many ideas to do the averages on the boundary side. So there are too many papers which I will not mention explicitly here. So people have discussed all possible ideas. So average over the Hamiltonians, CFT data in terms of the OPE, coefficients in terms of operator dimensions, states, average over states, average over observables, average over n. Okay, they're all many ideas, and there have been many successes. Okay, so in certain cases, when you do these kind of averages, you actually can recover the gravity result. Okay, and but there are also many conceptual and technical challenges when you do these averages. So so one fundamental challenge is that in the examples which come from string theory of the duality, for example, including for super Yang-Mills theory, there's no natural ensemble exists. And so now if you want to do really, if average has to be a fundamental description, and you cannot say, let me do this average for this class of theory, do that average for that class of theory, or do this average for this observable, and do that average for that observable. Okay, so whatever average prescription somehow has to be a universal. Okay, since this is such fundamental relation, and the average procedure should also be fundamental, should be universal. And also, even though if the average procedure may destroy your Lagrangian asymptotic structure, so as I mentioned earlier, this asymptotic structure comparison, you should compare them not order by order, but all subdominant saddles, everything. Okay. But if you have if you have family of CFTs, each of them have some kind of asymptotic structure, asymptotic expansion, when you average them, that may destroy this structure. So so this will present the technical challenge. And then we have many precise boundary and Bach matchings, all these BPS quantities and Wilson loop, all these countings, etc. They rely on individual theory, okay, with the individual gravity calculation. And so when you do the average, in general, you will spoil them. Okay. And the last thing, say if you do as the JT case, if the boundary theory mapped into the gravity is really some kind of ensemble average, then when you average a unitary theory, okay, if you have a family of unitary theory, you average them, the resulting theory will not be unitary. Okay, in general, you spoil your unitarity when you do statistical average. And then that will destroy one of the fundamental benefits we want from the holography. Okay, we wanted to understand the Bach unitarity from the boundary. Anyway, so these are the difficulties which the average procedure currently suffering. And so in this, and there's another problem with this relation. And this problem is much less discussed in the literature. So this is what I call erratic M problem. So this problem was hinted in the paper by Schoenecker and Witten in 2022. Then I tried to, I also emphasized a little bit in the paper in September. So the basic idea of this erratic M problem is the following. So on the gravity side, when we do saddle point expansion using this formal gravitational path integral, this formal gravitational path integral has a very specific structure, in the sense that the G-Newton only appears only in this single place as a coupling constant, and the path integral, the matter or the metric, they don't depend on G-Newton, and the action does not depend on G-Newton. Okay. And so this is have the sometimes called the Picard-Lipschitz structure. And then that leads to this kind of, this kind of structure. Then when you do the small G-Newton expansion, then leads to this kind of structure I mentioned earlier. Mentioned earlier, which is the saddle point structure. Okay, and so this saddle point structure, this kind of thing, is essentially determined by this structure of this integral. And so I will call this specific structure. So this structure depends on G-Newton in a very specific way. Okay, so here I forgot the 1 over G-Newton here. So here it should be 1 over G-Newton in the exponent. So this depends on in a very specific way. So I will just call this a smooth behavior in G-Newton. Okay, even though this is not the standard mathematically meaning of smooth. I just call this behavior by smooth behavior in G-Newton. So mathematically, this is called the trans series. Okay, essentially, it's a sum over a family of asymptotic series. Okay.
One question.
Yes.
Maybe this is irrelevant for the final point, but in the
path integral, in some cases in a DSCFT, G-Newton depends on something like n, being the flux of something, and then the action can also depend on that same parameter, right?
Yeah, no, but that's for the specific solution. For the specific, if you start with the action, then does not depend on it.
I was thinking of like
it is 5 versus 5.
Yeah, specific solution can depend on it. Yeah.
Okay.
So mathematically, this is called the trans series. So I have a very specific mathematical structure. Okay, it's a very specific mathematical structure. Another assumption, as I mentioned on the CFT side, is we have always assumed, maybe influenced by the 't Hooft Largian expansion, etc., and all these matrix integrals. And somehow the CFT also have this structure. Okay, also have this, if we use the terminology, that the CFT also have this smooth dependence on n, okay, on n squared. But CFT partition function is actually very different nature. It depends on n in a very complicated way. So the fields, fundamental fields you integrate over, they depend on n. And then your action, which is written as a trace, they also depend on n in a complicated way. And you need this trace n to get this n squared behavior. So of course we know why. It's because in the CFT, n is not just a coupling, even in the Largian limits, but also characterize a number of degrees of freedom. It plays a dual role. Okay, it plays a dual role. And then this makes, in principle, the n dependence can be complicated. Okay. And indeed, in some specific calculations, in the case which matching with the black hole macro state, so Greg Moore has emphasized many years ago that actually the Largian behavior can be very erratic. They depend on complicated arithmetics. And they can have very general behavior than this kind of smooth asymptotic expansion. Okay. So now the question is this assumption should we trust this assumption? Okay, somehow we have always been trusting this assumption. Yes?
But this paper by Greg Moore is not about large n, right?
No, it is about, but it's related. Yeah, it's related. It is related to the large N. It's related to the independence, but there they have it's yeah. In many cases, indeed, it's related to the charge, but those charges depend on N. Yes.
So, at what level do you expect this additional structure to start coming in? At some power law level in N, exponentially suppressed in N?
No idea. At the moment, I have no idea. I'm just right now explore this conceptual possibility.
Because it seems to me that a lot of the difficulty here comes with the limit, not with the largeness of N.
Oh, yeah.
So if I take some
it's a
large
limit.
N...
Yeah, this is what I'm talking about. Yeah,
Yeah.
you will see. You will see in the next slide. You will, indeed, yeah. Yeah, it is in the limit. Yeah, precisely in the limit. Just in the limit, you cannot write the expression like this. This is a very strong assumption, but I want to emphasize.
Because if we just take, for instance, something like the black hole spectrum, right? You take the limit naively, and it's continuous. And then a continuous spectrum can't tell the difference between whether it came from a continuous spectrum at...
Yeah, but that's a leading
which comes
order.
from an average theory versus
but that's
comes
a
from a
order.
discrete spectrum of fixed
Maybe let's wait a little bit. Maybe let's wait a little bit. Yeah, I understand your question. Maybe wait a little bit, you will see whether your question is addressed or not.
Okay.
Yeah. Good. So now the question is whether this assumption is too restrictive or not. Okay. And so seems like there's no principle which guarantees that this structure should always be true. Okay. So if I just give you an arbitrary function as some function of n, okay, there's no reason. Okay, I can always hook up a complicated function. There's no reason why this function should have this specific structure. Okay, so somehow hidden behind this assumption, there must be something very strong going on. Okay. So if the CFT partition function not always have this structure, and then these two sides then don't have the same structure, then that means then this relation cannot be correct at the fundamental level. Okay, then this relation cannot be correct at fundamental level. So now I will make a simple proposal to address both problems. Okay. So what I will do is I will make a postulate. Okay. Right now I don't know how to prove the postulate or check the postulate, but we can in principle check the postulate. Right. Right now I just make a postulate, and then we will explore the conceptual consequence of the postulate. Okay. And then I will show that even the postulate is very simple, but actually you can gain lots of conceptual benefits. So now I suppose, when you look at the large N limit of the CFT partition function, that the large N limit is actually more subtle than what we have always assumed to be such a asymptotic expansion. Okay. So let's assume, in addition to the standard asymptotic expansion, which we call the Z-smooth asymptotic expansion, there's some other structure. Okay, there's some other structure that you can separate the CFT partition function into two structures. Okay, let's just assume that. And then the first part, say, is our standard 't Hooft expansion, trans series, smoothing n, you sum over your saddle points. And then maybe there's something else. So right now I don't know how to precisely define this something else. So let me just define what it is not. Okay. So I say this part which I call erratic is the part which cannot be written as a trans series. Okay, just again, erratic is a name which I call this thing. Just like I call smooth to be this trans series. Okay, I call erratic to be this thing. Okay. So say if I want to speculate, one possible kind of this erratic behavior, say, is the kind of erratic dependence on n, which cannot be captured by the smooth 1/n expansion. Okay, which cannot be captured by this kind of saddle point expansion, including the complex saddle point. Okay. So so this is something in principle we can try to check if we do So now let's just postulate there's some additional structure here. And then I propose the new dictionary is that we should just identify the smooth parts, which does have this kind of trans-series structure as in the gravity case, and we just identify them. Okay, we just identify them. And to do this, then we actually, to match the this means that to match the safety expression with the semi-classical one, we need a filter to filter out this erratic dependence. Okay. And say you do a filter, you extract this smooth behavior. So imagine if we can really compute the CFT partition function exactly. Suppose we are powerful to take a larger limit, then we should be able to great detail, then we should be, if this assumption is true, then we can make the split, then of course this filter will be automatic. You just take this piece. Okay. So this filter is intrinsically defined, provided that the split is well defined. Okay. Good? So now to say in the one step, we say that the filter acting on the CFT partition function then should be identified with the gravitational one. So this F, implicit in the F is the Lagrange limit. Okay. Yeah. So that's the so that's the subtlety in the Lagrange limit I want to say. Okay. So this provides an intrinsic boundary definition of this. Okay. And now we can just say, in principle, this is something defined on the CFT side. And now you can, so I will show in the next slide, let me just mention very quickly now that when you apply filter to this factorized partition function, then turns out that the answer is not factorized. It's not factorized. So you have long factorization. Okay. Yes?
Is the split unique?
Right now, I don't know. Right now, I assume that split can be done. Maybe there's some ambiguity. That ambiguity should not affect, say, significant physics. Yeah. Yeah, this is assumption at the moment.
Okay, but it's not known whether it's
Yeah, it's not known. Yeah, yeah. I don't know. I don't know how to define these two pieces exactly at the moment. So even in the trans series, there is a room which you can put a constraint on. Say whether you want to have a resurgent trans series or you have some other trans series. Yeah, even within trans series, I can put additional constraints. So right now, I don't really have a precise definition of both terms. I'm just assuming. Let's imagine there are two structures. Okay, and let's imagine, in addition, what we always assume is one structure. Let's assume there are two structures. And let's explore its conceptual benefits. Yeah. Yes.
Do you expect that the erratic part will be subleading or same order, or you?
Oh yeah, it's okay to be subleading.
But it could be of the same order.
Can be same order, can be subleading. It depends on the series. Yeah.
Isn't this important in your analysis?
No, it's not important.
If it's leading order, it would dominate on the smooth part.
Yeah. You will see later that what this means. Yeah.
Okay.
Yeah. It's not important whether it's dominant, subdominant, exponentially small. Yeah. It's, as far as you have the you will see. Yeah.
Okay.
Yeah, I think will be clear. Yeah.
Okay, is this split between Z smooth and Z erratic in the CFT related at all to this same sort of split that happens for 2D CFT and like ADS3, RMT2 stuff? That's just a split between the modular average term and like fluctuations, or are these completely different?
I think they're different, and they're philosophically maybe connected, but at the moment they're different. Yeah. So let me just very quickly say the property of this filter just coming from the assumption that exists a split. So first, by definition, this should act as a projection. So if you if something is already smooth, you act on it again, and then of course it's still smooth. Okay. And if you have if you act if you act a smooth quantities, by smooth quantities, it always means a trans series. Okay, so if you act smooth things as something, and then you can take that smoothing out of this filter. Okay. And so these two, just by definition, from that existence of the split. But now I want to postulate a third property, which I cannot. It does not follow from the existence of the split, but I think it's a reasonable assumption. Is that this filter is a positive, semi-positive definite. Means that if you have a positive quantity, and when you do the filter, you should still get a positive quantity. Okay, so these are the properties of the filter we assume. Okay. And now, just with this property and with this structure, with this identification, and then this will address this average problem. Okay, and so this will address all the conceptual difficulties I mentioned earlier for the average. Okay, so this is a single theory, and this is a quantity which in principle intrinsically defined for single theory. You don't need to do average. And yeah, we'll mention the connection to the average later. And yeah, so it's everything we talked, everything, all the success before are preserved. Okay,
What do you mean by star?
Sorry? Oh, star just means complex conjugate. Yeah.
But partition function is generally real, right?
Oh yeah, no. I can insert operators. Yeah. Partition function here is more general. You can consider. Yeah.
But in more like Euclideanized context.
Yeah, elliptic genus, all these things you can insert. Yeah. Euclidean, you can insert operators, and then you have conjugate, etc. Yeah.
Question?
Yes.
When you write these equalities, are you assuming that the Thomp coupling is also taken to infinity, or this equality holds at finite Thomp coupling?
Yeah, should happen even at finite Hooft coupling. Yeah. Yeah, the subtlety is all in the n go to infinity limit, I think. Yeah, I think you can generalize this to string theory. If you can formally write down a string field theory part in the Go, etc.
But then from gravity we are
assuming that even when alpha prime is finite, we get this non-factorization.
Sorry?
From gravity, are you expecting that even when there are higher stringy corrections, there is connected part?
Oh yeah, I mean, right now I'm talking about in principle here. On the even include alpha prime correction, you may still have wormholes, etc. Yeah. Good. Okay, so now let's talk about how does this wormhole come into this story. So let's look at this CFT on this the disjoint union of two manifolds, and then by definition, at finite n is factorized, and the Z1 corresponding to the partition function of M1. And then, yeah, the F acting on Z1 then corresponding to the partition function of gravity with M1 as a boundary. And then, yeah, then the acting on the product of D1 and D2 corresponding to the gravity, the partition function, the G Newton zero limit with M1 union M2 as boundary. So now let me just introduce a simple notation, just call this so D1 is the full partition function. And remember this FZ1 is the smooth part, and the difference would be the erratic part, okay, what I call erratic part. And so by definition, the filter acting on the erratic part, you get 0. Okay, acting. But the key, okay, now the key is that even though naively seems like the filters throw away the erratic part, but actually it turns out that the information about the erratic part in principle still can be probed, okay, in the following way. So let's look at the F acting on this. So now if you look at this Fz, then each Z1, then written as Fz1 plus delta Ez1, and when you do this product, there are 4 terms under this filter, okay. And the first term is just the factorized term, and then there's a term like this, which corresponding to delta E, and then there's a cross term corresponding to delta E Z1 to the filter the Z2, okay. And those kind of cross terms, they're zero, following from that this is zero, and you can take the smooth part out. Okay, and so from that rule, you just get this. But now here is the key point. I have this erratic part delta Z1 times erratic part delta Z2, even though each is erratic. But it's possible that their product, okay, actually contains a smooth part. So for example, if I consider toy example, if you imagine so delta EZ1 contain some erratic phase in N. And imagine somehow this erratic phase have opposite erratic phase in the delta Z2. Then you multiply them, then they can cancel. Okay? And then their product that can contain the smooth part. And then that means this quantity actually can be non-zero. And then in this way, then FZ1 and Z2 is not factorized. Okay, FZ1 and Z2 is not factorized. So now you just identify the non-factorized part on both sides, and then we just identify this non-factorized the F on delta Z1 with the gravitational part integral, with the wormhole contribution. Okay. So with a slight abuse of language, we can call this as correlations among the erratic N dependence. So the delta EZ1 and delta EZ2, they are correlated if their product contains the smooth part. Okay. And then now we say this kind of correlation of what this wormhole captures is precisely this correlation among the erratic N dependence. So you have the partition function on M1 have some erratic N dependence, and the partition function on M2 contains some erratic N dependence. If they are correlated, and then the wormhole is the gravitational way to tell us somehow this kind of erratic part are correlated. And then the wormhole now is actually a window for gravity to tell us those erratic part presence, the presence of the erratic part and their physical properties. So on both sides, so this thing can be dominant or subdominant. So if this is dominant, then just means that your wormhole partition function dominates over disconnected one. And certainly, at least in toy models, gravity, there are examples like that. But here, I emphasize the identification between the two sides. You really should identify all possible saddles. Okay, and so it doesn't matter whether this is dominant or subdominant. Good?
I have a question.
Yes.
So one confusion I had was that one confusion I had was that this the F acting on the product of erratic terms, what you call the erratic terms vanishing, could also arise if you have a trans series with a complicated phase structure.
Yeah.
Right. Like so, in principle, you can also have this wormhole term coming from a by taking the norm squared of a very complicated trans series.
No. That trans series is encoded in this term.
But I mean, if suppose one only had the trans series.
Yeah. Then just encoded by this term. Yeah, you need two structure to have this. You really need two structure. You don't have one structure, then you just have one term. Yeah, you really need two structure.
But like in the Gutzwiller trace formula case, where you have very complicated phases, like can't one also? I mean, even though those saddles, the saddles with very complicated phases, may be, I mean. So
you have to be careful in different situations how you call the saddles.
Yes.
So in the Gutzwiller trace formula, you have this averaged piece, and then you have the piece come from the periodic orbit. And those periodic orbit, even though they come from some classical solution, but they are not the saddles of the partition function. They are some classical solution, but they're not saddles of the partition function. Yeah. Maybe we can discuss that.
Okay.
Anyway, so you can just trivially generalize this. If you have 3 of them, then you can just have the wormhole, okay, 3-neg wormhole. And I can, this C means connected one. I can also generalize, you can have, when I write M, I imagine you have heavy operating insertions or current or those things insertions, but you can also have light operating insertions and generalize them into light operating insertions. And then the general formula is that if I consider the general product of this N partition function, the erratic part, and then suppose they have a connected piece, and then that should be related to a wormhole, connected wormhole to all these N boundaries. Okay, these all N different boundaries. And so this, again, this gives you an intrinsic boundary explanation of the original wormholes and the prediction of their amplitude just by assuming, okay, by assuming this kind of structure. Okay. So, but actually, we can actually learn more. So right now, I'm not powerful enough to find this delta E ZCFT for you explicitly. Okay, so we should look at all the examples. But right now, I don't have powerful enough. I'm not able to isolate the example for you. But even without knowing this delta E explicitly, just this structure itself is already enough to put constraint on this wormhole partition function. Okay, so I will show that this identification actually have immediate implications. It predicts the infinite tower of inequalities for the wormhole amplitude. Okay, so let's look at it. So remember this X, script X includes both the manifold itself and all possible operator insertions on that manifold. So that's our data. And then for each such data, if you look at the erratic part of the CFT partition function, you get some, say, erratic piece. Okay. So now we can just view this thing as a function on the space of all these X configurations. Okay. And then the products, you can take the product of them. Of course, they compute, they're just numbers. And together with complex conjugation, they form a commutative star algebra. And now if you look at this filter, what this filter does is take each element of such a algebra, you have such a product, it gives you something smooth. Okay, remember when we call something smooth, it's the space of a trans series. So in the algebraic terms, such kind of operation defines a state, okay, on the algebra. And this state is valued in this space of a trans series. And now then there's a standard theorem in the algebra, in the abstract algebra, saying if you have an algebra, then you have a state, okay, and then you have a Hilbert space. Okay, then you have Hilbert space. So this is called the GNS construction, and then you have a Hilbert space. And in particular, this positivity property I mentioned earlier for F ensure that this Hilbert space has a positive inner product, okay, non-negative inner product. And now we have a Hilbert space, but this Hilbert space is not the usual one, okay? It's the vector is valued in the space of trans series. But still, yeah, but that's not another problem because the space of trans series is mathematically a field. Anyway, so heuristically, what this Hilbert space does is associate each element of the algebra to a vector in this Hilbert space. Okay, to a vector in this Hilbert space. And then, for example, the overlap between these two vectors, so this is the simplest vector. You only have one partition function. And the overlap between these two vectors just given by the filter of the product. Okay, just by the filter of the product. And then that in turn relates this amplitude to this wormhole in gravity. Okay, this overlap. Okay, so now when you have a Hilbert space, then you have Cauchy-Schwarz. Okay, you can check that you can generalize Cauchy-Schwarz to this more general case with the defined on the trans series. And in particular, the space of trans-series has a real part, a real subspace, which you can define the ordering. So you can talk about the smaller or bigger. Okay. And then, for example, the Cauchy-Schwarz inequality applied to the state implies such an inequality for the wormhole amplitude. And again, I emphasize that this inequality is based on the trans-series. Is how you compare with the trans-series means that, remember, both sides are divergent series. Okay, they're not defined as numbers. But you can compare them based on their dominance in the large N limit. Okay. And so this is a highly non-trivial inequality on the wormhole partition function, which you can in principle check. And so
a question: when does it saturate?
Yeah, I don't know when does it saturate. It just saturates when this Cauchy-Schwarz inequality saturates. It's some properties of the wormhole which I don't know how to describe precisely. Yeah, I don't know how to translate that into specific property of the wormhole at the moment. So, but this group, they have actually come up with this same inequality from completely different motivations. Okay, so they were thinking about gravitational path integral. They want to define some positive definite thing for the gravitational path integral. Then they come up with this inequality, and they have checked in various non-trivial examples. Okay, and so they're more powerful than and they have checked some non-trivial examples. But in this case, we can actually have infinite number of such inequality. Just look at more complicated states. And then, for example, you can have this 1, 2 wormhole to 3, then it's smaller than 1, 2 to 1, 2, and 3, 3. Okay. So I emphasize in this kind of equation, you should include not only connected part, but also disconnected part. But there's no tadpoles, okay, because by definition, the wormhole does not include the tadpoles. Anyway, so you can just, and actually in the case of the JT gravity, Cynthia Yang have helped to check some of these inequalities in JT. So actually later I will, maybe there's no later. So maybe I don't have time. So I will actually interpret this Hilbert space. This Hilbert space is actually not actually just a completely abstract mathematical construct. Actually has a very clear physical interpretation. You can interpret this Hilbert space as the semi-classical Hilbert space of all isolated closed universes. Okay. And then this kind of inequality essentially just comes from this kind of Cauchy-Schwarz constraint on the transition amplitude between different closed universes. Okay, so so this Cauchy-Schwarz relation inequality also have clear physical meaning. Okay, so let me now maybe make some remarks. So the first is that in our discussion, this relation still does not change. Okay, it's not like in JT. When you write in the JT, the gravity partition function will correspond to some average of the CFT. But here, at the finite n, this relation is intact. Okay, at the finite n, we still believe this expression should be true. At least we see no indication anything should be, something wrong should be here. But now what we are saying is that in the G Newton goes to 0 limit, actually the current thing we have been doing is this filtered relation. Okay, and you filter on both sides. So what I want to say, what we have been doing on the gravity side has always been implicitly doing some kind of filtering. It's because if you follow the Gibbons-Hawkins, say, the semi-classical limit of the gravity is just given by the gravitational path integrals defined as a device for saddle point. I want to claim that procedure already has done some level of filtering. Okay, it's because we know from the Parkinson-Hawking, from the interpretation of the Parkinson-Hawking as the entropy, and also string expression principle, etc., that in full quantum gravity, G Newton also not only controls the coupling, but also the number of degrees of freedom. Okay, and so by by resorting to gravitational path integral, say G Newton goes to the limit, that this partition function should be given by the gravitational path integral with set point. That, I want to say, we have implicitly already done some filtering. And right now, I'm just trying to point it out, maybe there's some, there's something on the CFT, there's something on the CFT side. Okay. So now let me just make some comment on this factorization in the G Newton goes to zero limit. So if you believe this expression, so this expression is factorized for M1, for M equal to M1 using M2, and should also factorize if you take larger limit. Okay, the full expression when you include the erratic part, it should factorize. So that means that the gravity side, when you take G Newton goes to zero limit, should also factorize. Okay. But previously, it's not clear whether this, on the gravity side, is due to the breakdown, say, of the semi-classical gravitational path integral approximation, or due to you need to include, or you need to exclude the wormhole contribution. Okay, and there are many possible ideas. So here, what we are saying is that Euclidean path integral is valid within its own domain of applicability, means that it's a set point, give you certain contribution of the set point. And the wormhole saddles, they definitely should be included, but not only they should be included, they're actually very important. Because they give us the windows into the erratic dependence on G Newton. Okay, erratic dependence on n corresponding to erratic dependence on G Newton, and that's what this tells us. So that means that so this also highlights we need to understand the gravity counterpart of this erratic part of the CFT. So whether that means to include some things beyond the ordinary saddle point in the path integral, say maybe you should include, say the simplest possibility one may imagine, say is include some off-shell configurations, some singular configurations, etc., etc., or maybe something more. We don't know at the moment. But this highlights that somehow maybe there is something on the gravity side. Yeah. Okay, so now let's mention the connection with the averages. So as I mentioned, there have been many discussion of the averages. They have many successes. Okay, you average over the CFT, say OPE data. You average over the, we have heard on Gongxiu yesterday. You have you average over the dimensions, etc. Okay. And so they have, and then you can compare with gravity, they seem to be very successful. So let's try to interpret what that means in this context. So, 1 second. Okay, so we have this split. So what I claim is that somehow if there's a fundamental split like this, then that also provides a very simple way to understand why average works. Okay? So the discussion here is consistent with the discussion using the averages. It's because once you know this piece exists, then you can just use whatever method you can have to extract this piece. You don't have to really take the angle to infinity limit, find this split, okay? So now maybe you can find other tricks to extract this piece directly. Some of the tricks, including, say, for certain series or for certain questions, you can design some specific averages so that this part does not contribute, okay? And then you automatically extracted this part. So I claim that's what people do when people are doing averages, okay? So, and in particular, there may exist multiple different averages to extract this smooth part. Okay, the method does not have to be unique. And so this is like in statistical physics. If you know certain quantities are universal, and then you can do cross-graining, okay, to extract that quantity. But the cross-graining, the details of cross-graining or specific cross-graining is not important. Okay, as far as you know that the quantity is universal. And so here we are saying something similar. So here I want to say, here here our proposal just give a fundamental and universal way to define this piece. But this does not have to be the most efficient way to extract this piece. Okay. Good. So far I've been talking about the Euclidean story, but you can naturally ask, if we change the Euclidean story, then what happens to the Lorentzian story? Okay, so now first let me just remind you what happens to the Lorentzian story of conventional wisdom. So we have a boundary, we have a Bach Lorentzian. So in the Lorentzian, we normally start with the Bach Lorentzian space-time. Okay, Lorentzian manifold M. Then we say, oh, if this is the solution to the Einstein equation, say for example black hole, etc., then we say this must be described by the large N limit, say for a sequence of the boundary states for each n, and the large N limit of this state should be described by this Lorentzian manifold. And in particular, the observables in this psi n can be expressed in terms of semi-classical gravitational quantities. Okay, say like entanglement entropy, real-time correlation functions, etc. You can also ask this question in the opposite direction. Suppose I give you a family of such states for each n. In what sense we can say actually in the large N limit, this actually describes the emergence of some kind of Lorentzian spacetime, macroscopic Lorentzian spacetime. Okay, so how do we know that it actually describes a semi-classical, has a semi-classical gravity description? So the working definition, using the conventional wisdom has been the following. So let's look at the connection of all the single trace operators, which they can be defined in the large N limit. And then we look at this correlation function of single trace operator in this family of states. Take n go to infinite limit. And by this limit is well defined, we mean that this correlation function factorized as we expect for the to map with the gravitational ones, and also say the 3-point function is suppressed, 4-point function is suppressed, etc. And the 2-point function has a well-defined limit when you normalize this O property. Okay. And so if this is well-defined and satisfies all those properties, and then we say it has a well-defined semi-classical description, presumably describes some gravity background. But now with our new Euclidean dictionary, clearly this Lorentzian dictionary should also be modified. Okay. In particular, I will argue this leads to a more general way to understand the Lorentzian emergence. So let's imagine we have some Lorentzian observable G, which can depend on n in some state psi depend on n. And then again, we can say imagine n go to infinite limit, they separate into smooth and erratic part. And again, the smooth part, yeah, here the situation is even less clear. It's because the Euclidean you can define the using path integral, etc. So Lorentzian the path integral is a little bit harder to define. So the trans series maybe even more subtle to define. Okay. So again, right now I'm just postulating there's these two structures. So again, I postulated these two separate structures, smooth and erratic part. And again, the proposal is that you can add a filter to project to the smooth part. And then that is identified with semi-classical gravity without. Using our normal, again, the saddle point approximation, etc. And then this also leads to a larger idea of the filtered Lorentzian emergence. Is that instead, if we consider this family of states psi n, and then we say it has a semi-classical gravity description, if this now the correlation functions of single trace operator in this thing, they don't need to have a well-defined large N limit in our previous sense. Only the filtered part, okay, should have a well-defined limit. In the sense you should factorize, you should suppress by 1 over n in a certain way, etc. Okay, have 1 over n scaling in a certain way. And then this, in principle, leads to a more general way to understand the Lorentzian emergence. And so the examples is I claim are the closed universes which appear in the ADS can be understood this way, and also black hole interiors can be understood this way. Okay, And yeah, okay. So I think I'm already at the time, so let me just say my plan for the talk. Then I can stop when I finish the plan. So so the conjecture. So if you believe this proposal, and then now we can try to see what insight we can get from here. And because people have already studied lots of wormholes, lots of wormhole study and averages, etc. We have already accumulated a lot of knowledges. So we can actually use those knowledge based on the proposal to make conjectures on the erratic independence of Euclidean partition functions. Okay. So that will give us hint where to look for this kind of erratic dependence in the Euclidean partition functions. Okay. And so there's various things I can say here. And also, so I want to give examples of this filtered Lorentzian emergence in terms of closed universes. So there are two types of closed universes you can think about. One is the isolated closed universe. So these are corresponding to space-time. You just have closed universes without boundaries. Okay, there's no boundary. And then another type is that the closed universe entangled with some portions of ADS. So I want to emphasize that these two are actually conceptually very different. In the second, because you have a boundary, okay, there's ADS part has a boundary, you can actually, in principle, assign a CFT state to define this configuration, okay, to define this kind of a gravity solution. But in this case, in isolated closed universes, there's no boundary. So there's no, I would say there's no CFT state you can associate with such kind of closed universes. Okay, there's no intrinsic finite n CFT states you can assign to describe this kind of isolated closed universes. So I claim for this kind of closed universes, we have to use different methods. So maybe using some algebraic method, etc. Okay, and then finally, you can argue that the black hole interior can be understood. So if you have a typical long black hole, then you can argue that this black hole interior for such a long black hole actually come from this filtered Lorentzian emergence. Okay, I can stop now, and then, people can ask questions.
Do you expect this erratic behavior in BPS sector?
Yeah, it may. We don't know at the moment. I think, it can happen in the BPS sector. Yeah. In principle, yeah. Yeah, I think we should examine them. I think the BPS sector is our simplest starting point because we have accumulated a lot of finite n partition function, and so we just need to analyze them. Yeah.
There are some partition function we know that there's no erratic part, and then does that mean Rho's boundary configuration cannot involve in any wormhole?
Yeah, exactly. Yeah, exactly. Yeah, actually, I was going to say, for example, one example is the thermal partition function. So I would claim the thermal partition function does not have any erratic part based on this proposal, following a theorem of Witt and Yao. Yeah.
I kind of just come back to my previous question. I wasn't seeing. I guess can you elaborate on how this is, on how the split in CFT2 is not a specific case of this?
Yeah. So you see, this is related to my statement that in the thermal partition function for CFT2, actually there's no erratic part. Yeah, let me just elaborate on that. So there's so if there's an erratic part, then that means there should be wormholes connect that part. So if there's no wormhole, okay, if the Euclidean manifold never appears as a boundary in any wormhole, and then that means the erratic part must be zero. Okay, and in the case of the thermal partition function, there's a theorem by Witt and Yao saying that kind of S d minus 1 times S1, they don't have, they cannot appear as the boundary of any wormhole. And so at least in the simplest thermal partition function, and this erratic part, I think, should be 0. Yes.
Emil first. One.
I'm confused by that last statement.
Oh, you mean this statement?
Well, no, the statement that there's no erratic part to CFT2. I mean,
Oh, okay. No. I'm not saying there's no erratic part to CFT to this particular partition function. CFT2 have many partition functions, but this particular S1 times S1 partition function without inserting any operator.
Sorry, the black hole spectrum is entirely chaotic, right? So I would have said there's a Carty spectrum.
No. The black hole, that's a microcanonical ensemble. That's a density of state. Here I'm talking about the partition function. Density of state definitely have erratic part.
You can get one from the other.
Yeah, no, but that's subtle. And when you do that Laplace transform, it's a subtle, may not commute with an RGN limit, etc. And all these subtleties can appear.
Okay. May I offer a comment? So you can take this partition function and analytically continue in beta. So you take
yes. When you analytically continue beta, then erratic part will appear.
Right, but well, I mean, we expect those things to be sort of analytic functions of the parameters, right?
No, we don't know the precise. You see, when you take the RGN limit, and then that analytic continuation and the RGN limit, they may not commute. Yeah, indeed, one of the prediction of this formalism is that if you calculate this for the thermal partition function, so the density of states must be such, okay? The density of states for this theory, which we know must be erratic when at the black hole level, black hole state, order n square. But the density of state must be such that when you do this simple partition sum with a real beta, there's no erratic part. At least by erratic part here, I mean, say exponential n minus n square kind of suppression, okay? But you can maybe have even more, yeah. Anyway, so there's no erratic part, but if you look at spectral form factor, look at this thing with the beta plus IT, complexify this beta with a sufficiently large imaginary part. And then this erratic thing can appear.
Well, the true partition function is an analytic function of beta.
At finite n.
At finite n. The smooth part is an analytic function of beta.
Yeah.
So I would expect the erratic part also to be an analytic function.
I think that's obvious. You have to take the limit. Yeah.
It's an analytic function of beta, and then there is some.
So actually, so there's some unitary matrix integral you can try to do. So I'm not so. When you do such kind of analytic continuation, somehow when you go to complex parameter, things can become funny. For example, if you have a phase, and then the parameter, you have a real parameter in the phase, but then if that phase becomes complex, and then you can have exponential divergence, that leads to exponential divergence in the RGN limit. And then that means that kind of analytic continuation is it's subtle, yeah.
There was a slide you had where the last sentence was black hole interiors are emergent.
Yeah.
Can you elaborate?
Oh, right, yeah, I can elaborate on that.
Do you mean it's something that's not there before you apply the filter, or what do you mean by emergent?
Yeah. So what do I mean in the following? Yeah, good. Somehow this thing does not always work. Okay, so what I mean is the following. So normally, we say that if you look at the black hole, say let's look at the non-black hole. A structural black hole is a degenerate special case. Let's not worry about it. Let's look at the non-black hole, which is a more typical one. So normally we say the operator outside the horizon is just described by single trace operator on the boundary, so we understand very well. But the operator inside the horizon, and they're described by this modular flow operator. And this modular flow operator is the But those modular forward operator can, in principle, have complicated independence. But we do know somehow their correlation function, somehow they must behave in a way which leads to a smooth behavior, like some field, smooth field inside the horizon. And so I claim this is through that filtering. Even though the operator is not well defined, etc., but somehow this filter procedure makes that thing well defined. Yeah, so what the gravity sees, the gravity geometry sees, is the filtered part of this, correlation function of modular forward operator.
I have a question about the number 2.
Yeah.
So for the isolated closed universes, the Hilbert space would come from the GNS construction you would define, you discussed, right?
That's right, that's right. The first line, that's right.
The first line.
Yeah.
But I would expect the second line should be basically the same thing, in the sense that most of that, these examples, you can tune the amount of entanglement you have, and you can make it very small. So it's basically the same as the first example, with some decoration of the extra, states in the ADS region. So
I think that's a very good point. But somehow, I'm still confused by that question. It's because, at least in this case, we can definitely associate with a state. But here, I don't know how to associate with a state.
Well, but I think in the second case, you should associate it with a state which, part of that state is coming from the filtering procedure, and part is an honest state in the boundary theory. And there is some entanglement.
That's right. Yeah, that's right. Yeah, it's true. Yeah, but I think I think this one is a little bit better, easier to describe. I'm just saying this one, this one, I in principle say we know how to describe at the finite n. It's because I can just look at that state, say let's go to finite n, we say that describe this finite n, this closed universe at finite n. But this one, how to think about it in finite n, I'm a little bit more puzzled, yeah.
Yeah, I'm not sure that you will have that closed universe at finite n. You might have just the ADS states.
That's right. Yeah.
Two different description of the same state at finite n. So.
Yeah. Maybe. Yeah. Mm-hmm.
Can you elaborate on your comment that you said there is some filtering from gravity side also? Like, are you thinking like integrating some?
Right. Okay. Good. Yeah. So the statement is the following. So on the gravity side, so Gibbons-Hawking told us, say if you have a quantum gravitational theory, if you look at the semi-classical regime, and then we should be able to describe this semi-classical regime just using this gravitational path integral, formally used as a device to do set points. Okay. So that's what they claim. But if you think about it from our new understanding of string theory or quantum gravity, which we learned from ADS-CFT, that statement is actually a highly non-trivial one. It's because we do know that somehow the quantum gravitational theory is, have all kinds of things, string exclusion principle, all these kind of things. And somehow when you take G Newton goes to zero limit, then suddenly it becomes this gravitational path integral just to set point. That seems like a highly non-trivial assumption. Okay, I'm just now trying to, again, to try to say we should focus on that assumption to understand it better.
Hi. It seems that you can look at the filter as a map from Bordisms to the field of the field that's generated by trans-series elements. Could one think of this like a very weird, juiced-up version of a topological quantum field theory?
Sorry, say it again.
Oh, sorry. It seems that you can think of the filter as like a map from the space of Bordisms, the wormholes being seen as Bordisms to this funny field of trans-series. Could
Yeah.
one think of this as like some funny version of a topological quantum field theory, you know?
Yeah, I think there's some kind of, I think, similarity with that, but I'm not sure whether that's, I don't think the Buddhism is the right language to talk about the CFT partition function. Maybe in some, I think somehow, indeed, there's some flavor of that, but I think it goes much beyond that. Yeah.
Okay.
All right, unless there's any more pressing questions, it would be time for a coffee break. All right, we will reconvene at 10:45. Let's thank the speaker again.